is talking about my x values. Now, what possible x values do I have for this whole graph? Is there a break at all? This is technically going on forever in this direction. This is going on forever in that direction. So my domain is technically all real numbers, negative infinity to infinity. Okay, I'm using up all the x's because we're going in both directions. Range, remember, is my y values. So if I were to be looking at that, I never go below the x-axis. Okay, but I do hit it, right? If it's hard to tell from the graph, look at my equation up here. If I plug in a 0, I'm going to get 0. Okay, so I know that 0 is included. So actually, we're going to have a bracket now for 0 because 0 is included in that. And we go all the way up forever and ever to infinity. Okay? Yeah?
Why isn't 0 in the domain?
Why? Because it technically is. It's included. It's just all real numbers.
Oh.
So 0 is in there. We just don't write it because of the null. Okay? So notice the difference. Now we have 4 different intervals. 1, 2, 3, 4, all talking about different things. Okay? We have intervals for increasing and decreasing, and now we also have intervals for domain and range. Okay? So on a test, okay, or just in good practice, label them. Don't just write 4 intervals and not tell me what each of them are. Okay? Okay, you've got to tell me what each means. All right. Copy down this next little box. You might recognize some of this language from Algebra 2 because we touched on this when we did quadratics. But we're now going to talk about relative minimum and relative maximums. Again, these are very formal definitions, very fancy mathematical ones. It's okay if you don't understand what this means, just copy it. We'll talk about what it means. The visuals typically help with understanding these definitions. Okay, so when we look at graphs, I mean, we've seen a bunch at this point, right? And like the little black one I've drawn off to the side, there's always going to be what we call relative minimum and relative maximums. Think of it as our turning points, right? Graphs can have multiple of them. So, for example, if I'm thinking about my relative minimums, this would be an example of one, and that would be an example of one. Okay? Again, you can have multiple. It's okay if they're different. Okay, relative minimum, relative maximum. My relative maximum are obviously my ones that are higher. Okay? Those points also tell us a lot of information. That's why we talk about them. Okay? If we think about real world scenarios, a lot of information is held in those turning points. Okay? And whether they're minimum or maximum. So let's just look at number 1 here. It says determine the relative maximum or minimum of the function. Again, we did this in Algebra 2, so this should look familiar. But if I'm trying to find a relative minimum or maximum, first I kind of need to have an idea of what this graph is going to look like. This is a positive quadratic, so we know it's a right side up U. Okay, remember if it was a negative coefficient out front, it'd be the other way around, it'd be upside down. So that means that my vertex here is going to be considered what? Relative min or relative max?
Minimum.
Yeah, perfect. So this is going to be a relative minimum. And what's nice about quadratics is there's only one, right? Because it's not like this curves and goes on forever and ever. There's only one, okay? That also, we know, is always going to be our vertex for a quadratic. Well, that was really hard to say for some reason. Okay, so then remember our formula to find vertex of a quadratic? Back in Algebra 2, think way back. Find the x value specifically of our vertex.
X minus x1 or something.
No, you're thinking something else. That is a formula, though. Negative b over 2a, yeah. So this should look familiar in maybe one of two places. One, we learned in Algebra 2. Two, this is actually the outside part of the quadratic formula. If we were to take away our plus minus square root, this is what's left on the outside, negative b over 2a, okay? So that's where that comes from, actually, in our quadratic formula. But let's find our x-coordinate of our vertex using this. Okay, so remember our points are A, B, and C. So when I plug this in, I've got negative 4 over 2 times 3. Okay, I'm just plugging in my values from my quadratic. So I have positive 4 over 6, which simplifies to 2/3, okay? Now that's just the x, right? In order to find the vertex, I need to have an x and a y coordinate. So there's a couple ways. You could do this in your head, right? Because, well, let me back up. We're going to plug this number where? Where am I going to plug that in to find my y? Yeah, we're going to plug it in for x back into my equation. Okay, so I take my f of x here, and I'm just going to plug it in. So I have 3 times 3/2 squared minus 4. Ooh. Oh, yeah, sorry, thanks. 2 over 3. Okay, so now there's a couple ways you could do it. One, you could just do it in your head, okay? Actually, square these. You could type it by hand into your calculator. Just make sure you have parentheses around your fractions when you do that, so your calculator knows what you're trying to accomplish. The last thing you could do is type this into your y equals, and then just make sure your table setting is at 1/3, okay? So there's a couple ways you could have gone about that. When you're done, though, I think you should get, it's like negative 10 over 3, if I remember correctly. Let me double check that, though. Negative 10 over 3. Yes, negative 10 over 3 should be our y value. So my whole vertex is 2/3 negative 10 over 3. And then we're going to specify that even more because while we know it's the vertex, we also know that it's a relative min. Okay? Okay? So you could say, if I were to ask you, like, where is there a minimum? You say there's a minimum at, and then tell me that vertex. Or you could just label it like this, okay? All right, any questions on that one, finding our max or min? All right, that was from Algebra 2, so that should be kind of a review. Let's look over on the next page. We're going to talk about average rate of change, which we've heard that language before. Average rate of change is always talking about slope, okay? We've seen it in these fractions before. We've talked about change in y, change in x. But really, it's just taking the difference in my y values over the difference in my x values. Now, this is where calculus is going to come into play a little bit today. Okay? We've really only talked about slope when it comes to linear equations so far. Okay? So far, we have only seen slope with linear equations. Okay? No, you don't have to write that. But so far, we've only seen slope with linear equations. Today, we're going to start talking about average rate of change or slope with nonlinear equations. Okay? Now, what made linear, how did we consider something linear? What had to be true about its rate of change? Yeah, it was constant. Is that what you psychologists can hear? Yeah, it's constant, right? With the quadratic, is it constant the whole time? No, right? So this is where this is going to come into play. So, average rate of change. We really only have used the word slope, but I'm going to start using average rate of change because as we just talked about with nonlinear functions, my rate of change is always changing. Okay? So we're going to find average rates of changes between 2 points. Okay? So for example, I'm giving you two elements in my domain, and I'm asking you what is the rate of change between x equals 1 and x equals 3. Okay? In order to find slope, we need to have 2 points. So let's find 2 points from these domains. So I'm giving you an x value. So let's find its matching y. Okay? So if I were to plug a 1 into my equation, we'd get -1 squared plus 3, so we'd get 4. So in other words, 1 point on my graph is 1, 4. Now let's find the other point they want us to use. So f of 3, plug in the 3 minus 2 squared plus 3. I get 1 squared plus 3. So I get 4 again. So that one is 3, 4. Okay, well, I'll write it over here so it's nice and even. Okay, so in other words, they're asking us on this quadratic, what is the average rate of change between this point and this point? Okay, now we're just going to find slope with those two given points, just like we have, like you did in 2.1. Okay, so I'm doing 4 minus 4, take my two y values, over 3 minus 1. Okay, so again, all I'm doing is the slope formula right here. That's all I'm doing right now. Okay, so I've got 0 over 2, which gives me 0. So the average rate of change between these 2 points is 0. Okay? Any initial questions after seeing that first one? Okay, try our next one. Same idea, we're using the same equation. Then I'm gonna show you kind of what's happening mathematically when we do these. You need a scratch paper?
I was just gonna write on the back.
Okay.
Is that 3 missed over?
Yeah. 0 and 3 is what you're doing.
What'd you get? Your work, John.
I got 0, 7.
Wait, what?
Yeah, that's one of the points.
You're gonna find yourself, right?
Mm-hmm.
I knew that. I was just.
Okay, so now we have our 2 points, right? So we've got 0, 7. Find your other one. So plug in the 3 and find your second point. Okay, good. So now these are our points, right? 0, 7. Now, yeah, so now find slope using those 2 points. Oh, look over here. Perfect. Perfect. This should be a negative. Let me just.
It was 18 and 1.
Oh, this. Do we flip-flop our order? Oh, yeah. We need to put our 0 first if our 7 was first. All right. You should have gotten -1 for our overall slope. Here's my work finding our 2 points. We find our slope with those 2 points. Yes, sir.
It's 0 minus 7.
Let me see.
I thought you were supposed to take
I did like the y1 minus y3.
Oh, that's fine, as long as these are lined up. So since you did 3 first on the bottom, it works. Yeah, yeah.
Jamison needs some help.
No, I just thought we were supposed to subtract the points.
You are, but you said.
Kind of, just make your slope. So
Yeah, no,
what?
I did a 0 minus 7 minus.
Ooh, yep, there you go. Y2 minus Y1. All right. Now, let's talk about what the heck we're doing right now because it does. You okay over there? You looked very concerned. It does. So, did you put 4 first? Did you put the 3 first? Then you're fine. Doesn't matter order as long as those are first, right? Okay. Okay. So, again, let's talk about what the heck we're doing. So here's the graph, okay, of that function. Okay, that quadratic. Now you're gonna have to tell me because I just lost my screen. What was the first 2 points we were comparing? It was 0, right, and 3. Yeah, part B. Part B. No, part A. Sorry.
What is this tomfoolery?
1/4. Okay, so we found from here to here. That was our first ones we were testing. Notice in here, our average, like our rate of change is changing constantly. However, the average rate of change, what you just did was you took all of these points. This is the calculus piece. All these points have their own instantaneous slopes. All of them. You just found the average of all of them. Okay? So from here to here, if I were to take all of these slopes, okay, and find the average, it'd be 0. Okay? Part B, what did we find? Between what 2 points? -1.
Wait for the slope.
For part B. No, not the slope, the 2 points. It was like 0, 7 or something?
Yeah, 0, 7, and 3, 4.
Okay. So now we tested in between here and here what was my average rate of change. So now it would be you taking all these instantaneous slopes and finding the average. Okay? So mathematically, that's what's happening. We'll think about it visually. Okay? That's what you just did. All right, so now what I want you to do is I want you to try our word problem. You know how to do it. Okay? Read the word problem. I give you the function.
There's S's. What are these S's?
Okay? Seconds.
What?
S stands for seconds.
Oh.
Okay?
Wait, so did I just plug each one in? Like,
Yep. Do exactly what we just did. We're just not doing it in context of a real world problem.
wait, is speed in miles per hour?
Seconds, yep.
What does this say after and?
Average speed.
And 6 seconds.
Average speed from 1 to
So between 1 and 6 seconds. Yeah.
Should we do like one thing, right? So let's plug the.
Mm-hmm.
So should I do like every like 1, 2, 3?
Well, we only test these two, right? Between 1 and 6. So now that you have these are our points. So our first point would be 1, 16.
Okay.
And our second point would be what?
1,
Not 1.
or 6.
6, comma.
Oh, 6. 5.
Mm-hmm. And then use those 2 points to find my slope, like we did up here. Okay?
Thank you.
Mm-hmm.
How you got a terrible
That's all I got.
How are we looking over here? 112. Perfect. Put it in context, though. Write a sentence. I don't want to just see numbers. Okay? Give me the context. Write a sentence.
You should get one. Miss Dawn did. Jam should get his beard lined up.
I can't grow any hair on my chin. It's my chin.
Oh yeah, it's a trip set.
Hey, stop. I am recording, so.
Ow!
Wait, Is it like video or just audio?
Audio.
Oh, you're cooked, buddy.
All right,
Is the mic on you?
just through the iPad. So wherever the iPad is, picking it up. All right, here's my work. Okay. All I did was I plugged in my 2 seconds, 1 and 6, to find my points, found my average rate of change or my average speed, and then I put it in context, okay? The average speed for 1 second to 6 seconds is 112 feet per second. Okay? Any questions on this one? Real world problems. All right, we're going to switch gears and talk about something a little different. So any questions in general about finding our average rate of change? Nonlinear functions.
Yeah.
Yeah.
Why is this 6 seconds? Oh, wait. For 1 second to 6. Oh,
Yep, so I tied 1 and 6.
I thought that was like, I didn't think that was 1.
Oh,
I was like,
okay. All right, we good? All right, the next thing we're going to talk about is going to be very similar to symmetry, if you remember doing that. I know some of you guys hated that. Okay, but remember our x-axis symmetry, y-axis symmetry, and origin? Very similar idea. We're now just going to put some names to those functions. Okay? So we determine that a function is even if for each x in the domain, f of negative x is equal to f of x. And then the function is odd if for each x in the domain, f of negative x is negative f of x. So again, very formal definitions. To make it simpler, if I plug in a negative x here, I want to get the exact same as f of x. Okay, so what I started with. So if I plug in a negative x, I should get the exact same function that I started with. And then for odds, I want the exact opposite of f of x. Okay? So again, just putting some simpler terminology to those formal definitions. However, you remember how with the symmetries, we had to test like 3 different ways. We had to plug in a negative x, then we had to try a negative y, then we had to try both. This time, we just plug in a negative x regardless. Okay, so we have a lot less steps than those symmetry pieces. Okay, so look at number 1. Determine if a function, or if the function, g of x is even or odd. Okay, so I don't know what it is yet, but I know that I have to plug in a negative x. So I'm going to take g of negative x, and now I'm just going to plug in a negative x everywhere that I see a regular x. Okay? So now let's just talk about how this simplifies. This is an odd exponent. So what's this going to end up as? Positive or negative? Negative. So it'll just be saying negative x3. And then I have a negative times a negative, which turns into a positive. Okay? So g of negative x equals negative x cubed plus x. Compare what I just got to my original. Is it the exact same? No. Is it the exact opposite? Yes. Okay? Because look at our symbols. Positive. Look at the board for a second. Positive, negative, negative, positive. Okay? My signs all flipped. So this is exactly the opposite. If it's the exact opposite, I know that it's odd. Okay? Let's try the next one. Look at number 2. Okay? So number 2, I'm testing h of x. Again, I'm going to plug in a negative x. I always plug in a negative x. Okay, so I have negative x squared plus 1. Now I have an even exponent. So what's that going to make my variable, positive or negative? Positive. Plus 1. Compare what I just got to the original. It's the exact same, right? Everything matches. So this is the exact same, which tells me that it's even. Okay? So let me just zoom out for a second so we can see it all. So both times I plugged in a negative x. When I plugged in the negative x up here, I got the exact opposite. Think signs there. When we talk about opposite things, we're talking about signs. Okay? And then down here was the exact same. Yes, Patrick?
Will there be problems where you can't just like look at it and know what it is?
Potentially, yeah. Yeah. Okay? If there will be some cases where it doesn't work out either way, it's not the exact same and it's not exact opposite. We just say neither there. Okay? So your answers would either be odd, even, or neither. Okay? Any questions on those two? Testing our negative x's. This is what we're going to practice. We've got a short little exit ticket. We're going to practice these problems. All right, last little bit here. This is it for today. The last thing when we talk about evens and odds is their actual symmetries. So this is how it connects, right? This is a throwback. Throwback to symmetries. A function is even if it is symmetric with respect to the y-axis. Okay? So if you can flip it over that y-axis and it's the same, that means it's symmetric and it's even. It's odd if it's symmetric with respect to the origin. So notice, which symmetry are we not talking about anymore? The x, okay? X-axis symmetry does not matter to us anymore when we talk about evens or odds. This is my little trick that helps me remember this. Think it's odd, it's got origin symmetry, and it's opposites, right? We want the exact opposites, all the O's, okay? We've got odd, origin, opposites, okay? Odd, origin, opposite. Evens is everything else, okay? All right, any questions for me on that last little bit we just talked about? All right, like I said, this is what we're going to practice today. So in your packet, we've got 2 pages, 14, 15. They shouldn't take you long, okay? Looking at 14, this is where you're really going to use, okay, where is it symmetric about? The y, the origin, or neither. Okay, that's how you're going to tell me if it's even or odd. Page 15 is where you're going to test it algebraically. So this is where you're plugging in the negative x. Okay? I want you to take pictures of this one. That way, because it's 2 different pages, like it's not front and back in your packet, because our notes are going to have to be on the next page tomorrow. So please either take pictures or show me at the end of class. Okay? So that we don't have to rip out any pages today. Okay? But that is it, notes-wise. Yeah. Yep. 14 and 15. Yeah. Yep.